Welcome everyone. My name is Magdy. I'm a software engineer at AWS, and I'm the author of the C++ Runtime for Lambda. And I want to talk to you today about how we got C++ to work reliably on AWS Lambda. But before we start, just to clarify a couple things. This talk is a mini deep dive. It is not a tutorial or a walkthrough. It's also not a sales pitch for AWS Lambda. So, though it's a great product, but that's not what this talk is about. An overview of how this talk is going to go. First, we'll be talking about what AWS Lambda is and what it can be used for, and what's this whole serverless thing is all about. Then we'll go over a bit of history on how AWS Lambda has changed over the past few years from an architecture point of view. And then we're going to start specifically talking about the C++ runtime for Lambda and the problems that we needed to get around to make it work. And then we'll end with why you would want to use C++ with AWS Lambda. So first, what is AWS Lambda? It's a service that lets you run your code without worrying about provisioning machines, configuring auto scaling parameters, or adding load balancers. You basically upload your code, and Lambda runs it and scales it up and down as needed. You only pay for the amount of time that your code is running. When your code is not running, you don't pay anything. It supports triggers based on events from other services, for example, or time-based events, think cron job, something like that. There are some constraints, though. It only runs on 64-bit x86 Linux. And your code has a timeout cap. It has to finish under 15 minutes. And there's also memory constraints. The maximum memory you can use is 3 gigabytes. You can configure it to use less, and obviously the less memory you configure it, the cheaper it becomes. So to understand the C++ runtime, we have to go over a little bit of history, and I promise it's not going to be long, how Lambda used to work in the past and how it works today. So before November of last year, Lambda supported a few languages like Java, .NET, Python, and Go. And those languages were added incrementally over the years since Lambda launched back in 2014. However, developers are, I guess, never happy or satisfied with the current languages. They always want their favorite language. And it became evident that it's not a sustainable model to just wait for the next year until my favorite language is supported. Lambda adds support for it. So in 2018, Lambda announced something cool known as the custom runtime, which basically is an HTTP interface to talk to the Lambda host. So if you want to use your own language, then all you need to do is write a little custom runtime that talks HTTP to the Lambda host, and then you can upload your code in that language and use the runtime, and the problem is solved. And the way it works is it's a get HTTP request to the Lambda host to retrieve the job that needs to be executed. And once you process it and once you're done, you post back with the response and the result of your job. And to illustrate this is a rough graphical representation of how it works. You have your application code, and the custom runtime is bundled with it. And the custom runtime will do the HTTP communication with that local endpoint over HTTP. This is not going across the internet or across the network. This is living in the same host. It's just it's just everybody knows how to talk HTTP, so this is why it was chosen that way. And then all the user has to care about is writing the application logic and a couple of functions to invoke in the runtime library to do the HTTP communication back and forth. So that's it for the history. Let's take a look at how the C++, specifically the C++ custom runtime looks like. So this is a hello world using the custom Lambda runtime, and starting with main down there, you can see that we have a function called runHandler, and it takes a function name, and that function, all it has to do is just abide by that signature, which it takes an invocation request, a constref invocation request, and it returns an invocation response. In this example in particular, we are just doing a hello world, so we're looking if the incoming payload has the literal hi, then we say, okay, it's a success. We return a hello world as the payload of the response, and we say the content type of this is application text in this particular case. And if it's anything else, then we say, okay, it's a failure. We provide a message and we provide an error type. In a real-world application, you would be expecting structured request input like JSON or XML, and you would be doing your processing and returning back also structured output like JSON or XML. Obviously, it can work with binaries as well, or if you want to send an image and get back a resized image, for example, or some filtered image, that would work as well. I'm just giving you the silliest example. It's important also to see how the package that the user upload is laid out. The application code and the custom runtime are packaged together in the same zip file. Lambda looks for a file named bootstrap by convention at the root of the package, and it executes that file. Lambda does not know or care about what this file is actually, what the contents are. It can be an ELF binary, it can be a shell script, anything that is executable. And this is gonna make sense later down the slides why I'm mentioning this. But once Lambda executes that, it sits down and waits for your code to call it back with that GET request to provide you with details on the next execution, and so that you can pick it up and do the processing and respond back. So at this point, we have a rough understanding of the mechanics of how a custom runtime works with AWS Lambda. Now let's talk about why getting this to work with C++ was particularly tricky. There are a few problems when you build a C++ application on one Linux machine and you try to deploy it on another slightly different Linux machine. Maybe a different distro, maybe a different version. And the reason usually is, and the bane of developers, is dependencies. Any C++ application has three types of dependencies. It has application-specific dependencies. It has the C++ runtime dependency, which is lib standard C++ or libc++. Again, we're talking strictly Linux. And then the final thing is the C runtime. And believe it or not, even if you didn't know this, the lib standard C++ and libc++ depend on the C runtimes. Even though your application is a C++ application, you still depend on the C runtime. So assuming that both machines have the same application dependencies installed on them, then still chances are they have different C++ runtime versions or different C runtime versions. It's a real problem, and we have to fix it. So as an example here, if you build your code on a development machine that's running Ubuntu 18.04 Bionic, which ships with GNU libc version 2.227, and then you deploy this on a machine running Amazon Linux 2017, for example, which happens to be one of the Linux hosts running, they run this distribution actually, which ships with GNU libc version 2.17. And when you try to run the executable, you're probably gonna see something like this. Symbol mismatch, even though, and you can see the symbol versions that they were introduced in glibc, and you get this annoying error. So this is the first problem that we have to fix, but there's more. The application dependencies. The other problem is application dependencies. On Linux, executables can have our paths or the paths to their dependencies embedded in the binary by the linker and in the form of our paths. And if you've been to Craig Scott's talk, Deep Sea Make, he touched on that heavily. So if those paths basically point to different locations, or it points to a certain location A on the build machine, but then you deploy it on the host machine and that location that is not a valid location, then you're gonna get such error. Can't find that library, don't know what to do. So to summarize, we have two problems to solve. And those two problems, if we solve them, we can make C++ run reliably on Lambda. So the first problem is figure out how do we package the dependencies reliably. And the second is how do we resolve the conflict between the system dependencies on the build machine and the system dependencies on the host machine. It should also be clear from this why other languages don't have this problem. Java, for example, or any managed runtime, they have a JVM and they only target that version. And .NET, they have .NET Core and they target that version. Same goes for the other languages as well. So only native languages are the ones who have to deal with this problem. So I'll walk you through some of the solutions that we tried, and then we're going to end up with the solution that actually we have working. And the first thing we tried is to use LDD and to get a list of dependencies from a given binary, and then copy those dependencies with their respective paths and zip them up in a directory. So it would look like this when you look at the package, basically. And this would maintain all the R paths that are embedded in the binary. And we would take that, on the Lambda machine, we would unzip it and overlay it on the Lambda machine, basically overriding libc and libstandard C++ and all those system dependencies. Kind of gross. So it actually did work, but believe it or not, this host, all the other agents and applications running on the same host, like metrics and logging agents, everything was hosted except the Lambda. So obviously this is not a good solution. The next solution is, okay, what if we, let's just forget about the R path and do LD library paths. So we run LDD, we add the files to the zip, but we put them flat under one directory, and then we set LD library paths to that directory, and we execute the binary. In this solution, we don't have to maintain the paths of the dependencies in the zip directory or anything like that. We just set the LD library path and we run, but this did not work because of the system dependencies problem that we mentioned earlier. So libstandard C++ is linked against a different version of libc, and it's just, we're gonna get that symbol mismatch error. All right, third solution, run LDD, add the files with the respective paths in the zip file, and then unzip it, and then chroot that directory. If you're not familiar with chroot, this is from the man page. It's a Linux command utility. You can run it, and you give it two things, a directory and a command, and it will make that command run under that directory as if that directory was root. This basically isolates the binary from anything else on the system. So this is basically what we would do. We would run, here's the package, and we'd run, as you have to run chroot as a root, and you run this command. This did not work because it actually almost worked again, but it did not work because Lambda needs a writable, it gives you one writable directory that your code can write to, which is /temp. And by default, Lambda mounts that directory on the host. So if we run within a chroot, then we don't have access to that directory which is /temp. That means we would, one of the two things we can say, okay, with C++, Lambdas cannot write to disk, which is not a good solution. And the other thing is we can tell the Lambda team to do some special, casing or a special situation for C++ and treat it differently, but that also would complicate things for the backend. So we didn't go with that. Solution number 4 is to use LD library path, but put LD preload, and we put the system dependencies in LD preload. That way we can try to avoid that conflict of system dependencies. But that also was tricky because of two things. We have to put that in the right order of how the dependency in glibc is the dependency tree of the glibc files, which is not really known for us. And the other problem is we need to get the list of files of all glibc files. It's not just a single shared library, it's a bunch of files. GNU libc is not one file. So that's the other problem. So that also did not work, and it was, even if it did work, it would be very fragile just in case things change in the future. It would just start breaking. So the next solution that almost worked and got us really close is to run the binary through the dynamic loader. So we add the files flat again into the directory, and we unzip them on the host, and then we execute the binary through LD Linux, and it would look like this. The command would look like this. LD Linux.so, and then we would pass in the library path, and we would say the executable. And to give you more understanding of what the list looks like, this is from the man page of LD Linux. One of the options, LD Linux is a library, but it can be executed just like an executable. And it takes an option, some options, and a program to run, as you can see. And one of those options is a library path. When you do that, this supersedes the R path and supersedes LD library path. So basically, now your program is running scoped down to whatever path you passed in, and it runs through that. And this was great, except that we needed a reliable way to bundle glibc files with the user dependencies, because again, glibc is not a single file, it's a bunch of files. And it's actually not obvious at first because they do not show up in LDD. So glibc files, one of them is, for example, libc DNS, which will only get invoked if you're making some network calls or making any DNS resolution calls. So it does not show up in LDD. We don't know if we needed it. We can't just arbitrarily just start adding files to the zip. We needed a more reliable way to package glibc. So we got to this. I was talking to a colleague about this problem, and he told me, well, why don't you just query the package manager, and it will give you the list of files. And that little brilliant tip got us over that over the hump, and we got it all to working. So basically, the solution now is LDD will give you the immediate dependencies of your binary, but then we know that we need to package the libc and standard C++ with your application dependencies. And the way to get a reliable list of those files is to ask the package manager about the list of files of libc. So we do that, and we put both together, and we put them into the zip file, and we execute it through, again, the LD Linux shared library. So it would look, the final bootstrap file that we talked about earlier becomes something like this. So remember, Lambda looks for this file called bootstrap, and it executes that. So this is our bootstrap file. It's a shell script. And all we do here is we say execute the LD Linux shared library, pass in the library path, and then here's the application. And the trick was we packaged everything correctly because we queried the package manager. We asked it for the list of files. This way, we do not have any interference with the system libraries, and we are running exactly what we got from the user. So for completeness, there are 3 alternative solutions to get your code running reliably on Lambda. The first thing is works out of the box with the C++ runtime, and it does that for you. It queries the package manager or on your current build system, and it gets your dependencies and zip them together and run them. The second option, you need to opt into that, and there are some reasons that would make you go to the number 2, is you start by building on Amazon Linux, and all we need to do at that point is set the LD library path, because that's the system that Lambda uses to run on anyway. The third option is to use something like musl libc and set the LD library path as well. And musl libc is has the advantage of being a single file. It is not a set of files like GNU libc. So once that is linked to, it shows up in LDD, and you package it just like any other application dependency, and it goes into the zip file, and everything works as expected. So some known problems and limitations about this. First off, like dynamically loaded dependencies, anything that is loaded via DL open are not packaged automatically. You have to be aware of that. There's no way that we can find out, or at least no way that I'm aware of, that we can find out what packages you are dynamically loading. So if you know that, you have to edit the zip file yourself. The other thing is TLS certificates. They usually live under different paths depending on the distribution. So if I am using Ubuntu, it lives on a certain path, but Amazon Linux have the certificates living in a different path. You have to be aware of this, and you need to tell your HTTP client where to find the certificates. So libcurl, for example, has that option. Third is data files are not automatically packaged. So any configuration files, any resources like images, what have you, are not packaged by default. Packaging the entirety of GNU libc can actually make your zip file bloat. There are quite a bit of files. It's not tremendous, but maybe about 10 megabytes it adds to your file as your zip package. So that's something to be aware of. If your package is already large, then that's one reason to opt in for the second option I had before, which is build on Amazon Linux so you don't have to package libc. The last thing is debugging is a little bit of a challenge, but we're working on this, and it's going to get better in the future, where local debugging is actually going to work just fine using other tools like SAM CLI. All right. Why would I use this? Why would I go through the pain of using C++ on Lambda? Well, as with anything related to C++, it's always about speed, and it's always about lowering costs. So time is money, especially on Lambda, because it charges you by the amount of time your code is running, and also by the amount of memory that your Lambda is consuming. So if you finish faster, you pay less. But however, I'll be honest, Lambda is already super cheap. So unless you have millions of invocations, then it might not really make much sense. The other thing is SIMD is now accessible. You can write your function and just naturally write SIMD instructions that just like you would be doing it in a normal C++ application, and you can run it on Lambda and take advantage of that. This is harder if you're doing .NET or if you're doing Java or any of the other managed languages. I think they're getting better with that, but it's not as it does not flow as nice with C and C++. The last one, which my favorite personally, is now you can do web applications with C++ that are backed by Lambda. You would need to use something like another service called API Gateway to front that Lambda, and then you should be able to make HTTP requests. Every HTTP request results in a Lambda invocation. So this is not, the way you would use this is not that you would be building HTML strings in your Lambda. That's not how it works. You would be sending in requests in, again, like structured in the form of JSON, for example, and your Lambda would look up some records in databases or do some processing according to your business logic, what have you, and then send down the results also in a structured fashion. And this all flows over HTTP regularly. All the concerns that are usually pop up when people are talking about C++ on the web is security, my machine can get compromised, all that stuff. Well, Lambda runs in a VM. It's not a Docker container, it's an actual VM, which means it's even immune to attacks like Spectre and Meltdown and those side channel attacks. It does not apply to Lambda. Because again, you're running in a VM, so nobody's sharing the kernel memory with you. And then last thing is just, I want to tell you that some technical details about the Lambda runtime. It's open source, it's on GitHub. It uses libcurl to talk to the HTTP endpoint, to the local endpoint. It requires C++ 11 or later to compile it, but the user code and the business logic of the Lambda itself can be in C, C++ 98, C++ 03, or any version of C++ that you like. That your code can be in any one of those things. There's no restrictions as far as that goes. You can also use your favorite Linux distribution to build your code. We are not restricted to use Amazon Linux or any other flavor in particular. And that's it. Questions?
Hi, thanks for the talk. 2 questions. First, is it possible to just link everything statically in the executable and run that on Lambda?
It is possible, but we could not ask people to do that because that means not only you have to build your application statically, but all the transient dependencies have to be linked statically. To give you an example, if you're building an application that does image resizing and you're using Image Magic or Graphics Magic, well, now you have to build Graphics Magic as well as a static library and all its dependencies and so on and so your entire dependency graph has to be built as a static library.
Okay.
Can it work? Yes, but it's a lot of work for you.
Sure. And my second question is, I'm interested in actually the runtime. So when do you actually spawn the processes to reply to HTTP requests? And is there any latencies incurred by the whole architecture?
I don't have numbers, but I can tell you that it's local on the same machine. So you're not making any network calls. There's no packets flying out of the machine and coming back in. It's all networked, it's all in memory on the same machine. So is there latency compared to not having one? Sure. But is there latency that you can observe and actually see that it is costing you? No.
So do we agree that it's one process invocation per request? So you have to start a new process every time, right?
No. So that's a good question. So the first time your Lambda runs, it runs main, and then it runs your handler. And then from there on, the runtime will ask the endpoint, is there more jobs? And if there is, then it invokes your handler again. It does not go through main, create a new process. No. So if you have incoming requests in the pipeline, it will keep invoking it.
Okay, thank you.
Yep.
Hello. I have a question about SIMD. Actually, one of bullets on your slides were that we can utilize the SIMD, but in order to do that, we need to know what is the lowest CPU on which this will be run. Because if I compile my code, for example, targeting the Haswell, then I need some guarantees that it will always be run on Haswell or later CPUs.
Yes.
So what guarantees does Amazon
You can
have?
assume Skylake.
Sorry?
Skylake, the Intel Skylake.
Okay,
That's
thank
what
you.
you can program against, and this is guaranteed to be one of those. Your code is going to be running at least on Skylake or newer.
Thank you.
Yep.
So in your Hello World example, it looked like you were referencing some kind of Amazon-provided SDK for Lambda. Does that depend on any libraries in its own version of the C++ standard library? And is there a risk of conflict then?
Are you referring to the runtime header at the top?
Right.
Yeah, this is what this library does for you. So the runtime.h is the C++ Lambda runtime that this
No,
library.
but does that then make use of a C++ runtime library?
Correct, it does.
And that might be different than the one we retargeted to. So is there a risk of a conflict?
Well, the idea is that when you build your code, you're also building this runtime with it. You're not.
So this is just a header and that's it?
It is not a header-only library, but it's about like maybe 4 files. It's a really tiny library. So build it with your code and link them together. That's the.
So I compile it and link it.
Correct.
And
But even if your code that you want to run is older, like it's running C++ 98, for example, then you can build that, and you can build a C shim layer to build a runtime with C++ 11 or a more modern compiler. Then through that C layer, you can talk to older libraries.
Okay, thank you.
Yep.
Okay. I have 2 questions. One is how frequently the runtime queries for request, and the second question is like how does C++ runtime compares to like Java runtime in terms of startup times,
Right.
or even
So
Python?
to the first question, how often does it query? Well, once you post back your result or you run out of time, the timeout happens, then Lambda will see, do I have more jobs? Because the runtime will ask Lambda again saying, do I have more jobs? And if you do have more jobs, then it will give it back to you. I'm sorry, if it times out, then you time out. That Lambda invocation died, basically. It starts a new one. So it will only ask the runtime, to answer your question, it will only ask the runtime once this one is over.
Okay.
This does not affect scale, because if you have so many requests coming in, Lambda will scale up and it will start in parallel invocations.
Okay.
When does it decide parallel versus serial? This is like Lambda, there's an army of people working on that.
Okay.
All right.
Okay. So the second question is like how does the C++ runtime compare to Java runtime or Python runtime in terms of startup time?
I can tell you that it's the fastest. So in our comparisons, my comparisons and the Lambda team, it is the fastest.
Even with the HTTP request.
So There are, the Lambda team is migrating everything to use the custom runtime. So everything that is using the custom runtime is C++ is ahead of everybody.
Okay.
There is the older architecture where they use shared memory. Those are slightly bit faster, but this architecture is not, the future is going with the custom runtimes.
Okay. Thanks.
Yep.
Hello again. One more question. You said that you're not spawning processes each time a new job appears, and instead that you are reusing the same executable. But I'm curious, does that mean that our implementation of the handler must be thread safe, or do you guarantee that all jobs will be done invoked sequentially?
Sequential. They're all sequential. You don't have to worry about parallelism.
Okay.
For a given VM, there's only one request happening at any given time. Once that request posts back its result, then it gets another invocation. So there's not at any given time 2 invocations running on the same VM. If you send in 1,000 requests, then you're going to have 1,000 Lambdas running at the same time. Different Lambdas.
Okay, thank you.
Yep.
You said that you pay for Lambda for the time, for the compute time it runs, but you need to keep the endpoint alive all the time.
No, that's Lambda keeping that for you. So when you have an invocation, Lambda creates a VM for you that has the endpoint. And then you talk, the runtime will talk to that endpoint.
So we do not manage the endpoint.
Nope.
The Lambda manages it.
Correct.
Okay, thank you.
All right.
Are there any plans to fold this into AWS's Cloud9 editor to make some of these things easier to do as a developer?
I don't know, but that's a good idea. So probably should look into it. All right. Thank you guys very much.